Now let us look at this virtual memory implementation, at least in a very top level, high level view. Not we won't be going into much detail about inside the hardware logic circuitry much. We'll touch upon some, but we'll just want to have an overview of the virtual memory implementation and try to possibly exploit what is the implication for the operating system on that point. So let's say I have a virtual memory space. Okay, a virtual memory space means all the address available for that number of bits of the address. We divided the virtual space into pages. Okay, maybe it's contains like maybe n number of bytes or so and so forth. But let's say there are capital P pages. We divide the virtual memory space into that. Also, primary memory, okay, your RAM, the physical memory, they're also divided into pages, same page size as in the virtual memories. And let's say this is small p. Of course, your capital P is greater than small p. Your virtual memory has lot more pages there which can be virtually stored, whereas your primary memory can host only few of the pages, but the page sizes are same. Let's say if the virtual memory page size is 1 kilobyte, your primary memory also should follow the same concept. It follows the same concept from the on the primary memory. It's a 1 kilobyte of page, and then each page has blocks. Let's say this one page, 1 kilobyte, has 4 blocks in it. That means my block size is basically, we are talking of 256 byte, right? 256 byte of the block size, and 4 blocks constitute a page. All right. So this is the relation between the page and the block as in the cache memory context. Now what happened, a page table is maintained where we have a map between a virtual address and the physical address. Now physical address is basically what you have in your RAM. Now that means since RAM is smaller than your virtual memory space, some of the blocks, some of the addresses may not be or some of the page may not be on the RAM. They would reside on a disk. Okay, they would reside on a disk. So your map can point to either your physical addresses of the main memory or point to the page stored in the disk. Okay, that's the concept of the page table. Now what happened, a processor issues a virtual address, let's say it's a 32-bit address, and let's say it is an 4 kilobyte of page size. That's what like your offset value is from 0 to 11, which is 12-bit offset, which is like 4 kilobyte of address space. Then your virtual page number get translated into the physical page number, and that, let's say 26-bit of address, like just I want to make sure this is same concept as what we are doing in our project 2 and 3 as a processor memory access, like it's a 26-bit of address space. So here our page size is 4K, okay, and through the translate table, it's this rest of the 20-bit is changed to 14-bit physical page number, and the entire 26-bit consists of my main memory address. Okay, so if your main memory supports like 32-bit, we can say similar thing, that only translation is from 20-bit to 20-bit translation. Unlike here in this example, it is 20-bit to 14-bit translation. Now, what happens if the page is not in the main memory? it's a page fault, right? Then it will incur some penalty for the page fault. Page fault is costly because now we are talking of to block replacement from a very slow device, disk, right? It's a slow device. It's electromechanical device. If we are thinking of traditional rotational disk system, it will be slower. Now you can imagine if you replace your traditional electromechanical rotational disk with a solid state disk which uses the flash memory technology, your page replacement will be faster. So okay, you will actually feel or actually see the increase in performance of your computing system if you replace your traditional disk drive with a solid state disk drive, because one of the reason is your page fault penalty, it reduces a lot. Okay, and also page size is very important decision. Again, just like a cache block size, page size is very important decision, because like if you make the page size bigger, that means your page fault probability will be reduced. However, if there is a page fault, your penalty will be much more. Okay, and it will go other way if you shrink the page size. There are some key decisions in the designing of the virtual memory system to be taken. One of them, of course, your page size. It should be large enough to balance high access time. Reduce the page fault rate by using fully associative page replacement. This means like a virtual page can be placed in anywhere in the main memory. And that's a full associative replacement. Page faults are to be handled by the software, like operating system. Because we want to use more advanced and little complicated page replacement strategy to make more efficient decision. Okay, so it cannot be random, definitely. And least recently used also may not be very optimal. Okay, so in operating system, I hope you'll be learning about different page fault handling strategies there, and you'll come across many other strategies for handling, which is too complicated to be implemented on the hardware side. So it has to be handled by the operating system. And definitely write back is a strategy to sync content across the hierarchy. Write through is no, because you are writing on a disk, right? That's the slowest thing. So these are the key points that we need to remember. Now, this page table, okay. So what happens? There is this one special register called a page table register, has to be supplied through the hardware to the operating system. What happens here? Like these page table register point to the map, point to the virtual memory address, block address, virtual memory page address to the physical memory page address. It contains pointer to the map. So what happens for different processes, like let's say your system is running 50 different processes. So 50 different processes will have 50 different translation map, right? From virtual address to the physical address translation. That means we need to have a capability in the system to point to different translation map in context of the which process is right now active. So what operating system does when it switches the context, it basically changes the page table register content to reflect to the current process's translation table from the virtual address to the physical address. So it uses that map, and your virtual address now get translated, your virtual page number get translated from fully associated page table to the physical page number, if let's say it is there, and your physical address being accessed. And If 0, if there is none of these translation available for that specific virtual page number, that means it's a page fault. That means it's not in the main memory. We need to pick it up from the disk. All right.